In this lecture we're going to talk about the isentropic flow quantities and a normal shock. I'll bring my terminal in here to make a few calculations. What we're going to look at is an airplane, like when we looked at the SR-71 question. So here's the nose of the airplane. It's flying. Oops, sorry. The Mach number free stream, which I'll denote 1, is equal to 3, and let's use standard atmospheric conditions for, let's say, 11,000 meters. So we have T1. This is the static temperature of the fluid. I'll just round it to 216 Kelvin. Our pressure is 22.3 pascals, and we have density I'll skip for now. So we have these quantities. So if we think about a parcel of fluid, it has these properties as it flies through the air towards the plane. And so these are the atmospheric properties. These are the static properties of that parcel of fluid. Along with that, it has stagnation properties. What is the value of the stagnation pressure? So this is the pressure that this parcel would achieve if we were to decelerate it magically to Mach 0 isentropically. We'll go back to our calculator. So this is the isentropic Mach relations. Put in our Mach number. I see P over P naught is this number right here. So that's a pretty high pressure ratio. I'll do a quick calculation here. So P1 is equal to 22.3, and the ratio here is 0.027, basically, is about 36. So our stagnation pressure is 36 times our static pressure. So if we take that parcel from Mach 3, decelerate it to Mach 0 isentropically, the pressure is going to rise by a factor of 36.7. So I have P naught is equal to P1 times 36.76, which is basically that ratio that we get for that Mach number. It's a large ratio because it's a large Mach number, and I'm getting a stagnation pressure of about 819. That can't be right. Hang on one second. P1 was, one second. Pressure was 22,632. I had the wrong number. So the initial static pressure, I forgot it, is 22,632, and our stagnation is equal to that divided by this pressure ratio. So you get a stagnation pressure of 832 kPa. What about stagnation temperature? Looking at our isentropic calculator, again, we have T over T naught 0.35. It's a much smaller ratio. Our initial temperature was 216 Kelvin. So we have T1 216 Kelvin. So we have T naught 1 is equal to T1 divided by this ratio, 0.357. 605 Kelvin. Still quite hot. Okay, so these are all properties of this parcel. These stagnation values are the values if we bring it to Mach equals 0 isentropically. So these are not the properties of this parcel of fluid statically. So if we were to call, one of the difficulties is how do we actually measure the pressure of this parcel? If you put something out to measure it, you create a shock wave, you change the properties, etc., etc. So let's just pretend for a moment that the parcel can talk to us. It's flying along. We're here in this reference frame inside the airplane, and we call it on the phone, and we say, what's your pressure right now? It'll say, well, right now I'm Mach 3, my pressure is 22 kilopascals. My temperature is 216 Kelvin. But if you were to decelerate me to Mach 0, these would be my values. However, as this plane is flying, for a parcel to come impinge on the nose here and decelerate to Mach 0 isentropically is not possible. It's going to pass through a normal shock wave that looks something like this. The flow will pass through a normal shock wave. Across that shock wave, the Mach number will drop. It will become subsonic. The temperature will rise, the pressure will rise, the stagnation pressure will drop, and the stagnation temperature will stay the same. So what we want to compute on the other side of that shock are these quantities. So there's a couple of ways to do it. Let's start with pressure. So again, here's the streamline. Along that streamline, the slow is supersonic, m equals 3, and p is equal to 22.3 kPa. I wrote PA up there, I meant kPa. Whatever our pressure is. P1, 22.6 kPa. Okay, and then now it passes through the shock. What happens to the pressure as it passes through the shock? Well, we get another pressure on the other side of the shock, P2. What is this equal to? Let's go to our normal shock relations. Normal shock, incident Mach number 3. The Mach number behind the shock, 0.475. The pressure ratio across the shock, 10.3333. So we multiply P1 times 10.333, and we get 233,000 kPa. So that's the pressure rise across the shock. What is the stagnation pressure on the back of the shock? What is P naught to? The stagnation pressure has changed, and we can compute it in a couple different ways. The first is we can just look at the stagnation pressure ratio reported by the normal shock relations. Second is we can assume that once the parcel's passed the shock, its static pressure has jumped, its total pressure has dropped, but we have a new Mach number. We have M2 equals 0.475. So let's take this parcel, which is now here. If you call it on the phone, it will say, I'm now traveling 0.475 Mach, and my pressure is considerably higher. It is now 233 kPa. We'll go back here. Let's isentropically bring that from 0.475 Mach down to 0. The pressure ratio is this. This is the ratio of the static pressure to the total pressure behind the shock. When we have a lower Mach number, you can see the ratio is much smaller, 0.856. So now we can compute P2. We have P2. Now we want P naught 2 is equal to P2 divided by this ratio, 0.856. So P naught 2 is 273 kPa, roughly. That's the stagnation pressure of the parcel when it reaches the airplane. Is this value right here. Oops, sorry. Is this value right here. So we started Mach 3. This was the pressure. And we had a total pressure of, what was it? 832 kPa. We went across the shock. Our pressure rose from 22, or basically 23 kPa to 233 kPa. And we calculated using the isentropic relations. We took the same parcel, now moving Mach 0.475. With this pressure, we isentropically decelerated it using the isentropic relations and discovered at Mach 0, where it reaches stagnation pressure, we had 273 kPa. If you look at this ratio, P naught 1 over P naught 2, that's the stagnation pressure ratio across the shock. Let's just compute it. P naught 1 over P naught 2 is about 3. If you go back to our isentropic relations, normal shock relations, we have P naught 2 over P naught 1, which is the inverse of what we just computed, but you can see when I invert this, we're going to get 3. So we could have done it that way as well. Once we had P naught 1, we could have just used the normal shock relations. to get to P02, but we're not going to bother. So you can see stagnation pressure drops across the shock. This P02 is the pressure that's actually felt on the nose of the airplane. So once it gets here, the pressure on that nose when Mach is 0 and the reference frame of the airplane is P02. It is not P01. I hope that's clear. The second, let's just do the same with stagnation temperature. Here's the parcel moving Mach 3. The temperature of that parcel is the atmospheric temperature that we calculated. 216, call it 217 Kelvin. What is the stagnation temperature here? Again, we go to our isentropic Mach relations. We bring it from Mach 3 down to 0 isentropically, and we get our stagnation temperature. 0.357 is our ratio. So we have T1 out here was 217. We have T01, let's call it T01 for now, equals T1 over 0.357, 607 K. Now, the stagnation temperature across the shock does not change. It's going to be equal to T02 back here. Here's M2. But let's just see if the calculations work out correctly. Here's the nose of the aircraft. What is the pressure, temperature jump across the shock? What is T2? The temperature is rising across the shock. Let's go back to the normal Mach relations. Normal shock relations. Temperature jump 2.67. Come back here. 2.2 equals 2.67 times T1. So the temperature of the parcel behind the shock is 579 degrees. So it's hotter behind the shock. That's the temperature behind the shock of the actual fluid, but it's still moving Mach 475. Let's isentropically decelerate it from 475 down to 0. We see this ratio of temperature behind the shock, T2, to the stagnation temperature there is 0.956. So we have T02 equals T2 over 0.956. And we get 606. So it didn't change. T02 equals 676, 606, we'll call it 607. We've been doing some rounding here. Equals T01. The stagnation temperature did not change. So the parcel started, it had T01, passed through the shock, and it had T02 equal to T01. And then it impinges onto our flow solution here. So at this point, the parcel, the temperature of that parcel is T1, which is 217 Kelvin. It's moving Mach 3. Passes through the shock. Now it's moving Mach 0.47. The temperature is hotter of the gas. T2 was 579 Kelvin. It's hot gas. And then we slow it down to rest on the front of the foil here, down to Mach 0, and it rises a little bit more. Now, because it only rises a little bit because the Mach number is low. So we're only slowing it down a little bit. So we're only taking a little kinetic energy out, putting it into thermal energy. So our stagnation temperature rises above the static temperature, but only a little bit because we're at a low Mach number. But we already jumped the temperature across the shock. So we end up with T01, which is equal to T02, of around 600 Kelvin, which is quite warm on the front of this nose. And as we discussed, this heating, the thermal heating or aerodynamic heating, is really critical. And if you increase the Mach number, you see it's even more significant. If we start with the same atmospheric temperature of 217 K, and we increase the Mach number to, say, 5, you see the temperature ratio is 0.1666. Now we have a stagnation temperature of 1,300 Kelvin. So it jumps quite quickly with Mach number. It goes as Mach number squared. And so this thermal heating becomes a major concern in terms of structural and keeping things cool when flying at steady state, if you're trying to keep up with this for 2-3 hours. So in terms of hypersonic flight, heating, aerodynamic heating is really a major consideration. So I hope this sort of clears up this idea of isentropic flow. So it's just very important, just to recap. We have our airplane here. The airplane point of view is we're in the reference frame of the airplane. So there's a parcel of fluid here moving at Mach equal 3. The pressure and temperature of that parcel are equal to the atmospheric quantities. P equals P atmosphere, T equals T atmosphere. The stagnation values, which we compute using the isentropic Mach relations, are the values that parcel will take on if we decelerate it to Mach 0 isentropically. So we computed those. It's a function of the Mach number and the initial pressure, function of the Mach number and the initial temperature. But in reality, we have a shock wave here. When the flow passes through that shock wave, the temperature jumps, the pressure jumps, the Mach number drops to subsonic, and stagnation pressure drops. We saw it by a factor 3. The stagnation temperature does not change through that shock. Stagnation temperature stays the same. So T naught will be the same over here. We will need a new P naught, which we call P naught 2, and this is P naught 1. And P naught 2 is the pressure on the airframe when the fluid parcel is brought to rest. It is not P naught 1, and that is because we came through the shock.